Hello, this is my final video for Physics 105. Uh, so for this, I chose to draw my own machine, call it the milk machine. I'm just going to kind of explain what I mean to happen with the drawing, and then I'll go and break it down into the different parts of physics that are working within the machine. So it's going to start here, and I made this so if you don't want to take time to put milk in your cereal bowl, you can just let this contraption run and do something in the meantime. I don't know. So it starts over here with a little ball on this little like spring-loaded contraption, and there's a thing holding it down. So to let it start, you take the holder off, and it's gonna launch the ball up to this little stack of whatever you choose to use, books or boxes. And then it's gonna roll down each of these, and when it hits this little thing right here, this is a little elevator. The weight of the ball is gonna slide it down. It's gonna hit this block here. One part of it is it's gonna tilt the ball off of the little elevator, and it's gonna run into this bigger ball. And the bigger ball is gonna roll and go up onto this little spring-loaded platform here. Once it goes onto the spring-loaded platform, the platform will drop down. The ramp will fall off of it, and the latch holding the spring-loaded platform will fall off. And then once that happens, it'll launch the ball up here to this next platform, and it'll roll onto this teeter-totter contraption that is being balanced by this stick here. And once the ball is on there, it's going to roll across. Once it hits this point, it's going to tilt because it'll be heavier on that side, and the stopper won't let it go the other way. It's going to fall down. It'll tilt, and the ball will fall down and off and roll over, hit the milk, and the milk's going to fall over. The milk should be open. You have to open the milk first, and then the milk will pour into your cereal bowl. You will need to be ready to stop it, but theoretically it'll fill your bowl. So that's my milk machine. So I'm going to kind of go and break down the parts of the physics within this little contraption. So we're going to start. So once this ball is launched off of this first thing, it's going to be in free fall. And so it's kind of cut off on this paper, but I have it set. I have a y and an x axis there in my head that I'm thinking about. So it's in projectile motion, and it's in free fall. When the ball is flying through the air. So this also occurs when the ball is flying through the air after it's been launched to the side of this little platform as well. So when both times the ball is in the air, it's in free fall, and the only force acting on the ball is gravity, and there's no acceleration in the horizontal direction. So it's just being thrown, and it's moving in 2D, and so it makes a parabola path, so it goes over. So I guess I should mention I meant for this. I guess this latch doesn't fall. When this goes down, just when the ramp falls off is when it'll launch back up with the ball, and that'll hit it, and it'll tilt up and over. That's how it'll get over there. It won't, because if that didn't happen, it would just go straight up and down. So it'll hit that and go up and over, and so putting it in free fall. So yeah, that's the kinematic portion of my machine. So next I have, for my second, I have kind of work and energy here. I count this little elevator for like the work being done. It's gonna be negative work because the ball is pushing the elevator down, and it's doing negative work. And the potential energy the change in potential energy will be equal to the change in kinetic energy. And I also have the spring-loaded launch is kind of for work and energy. So when that thing releases it, it's doing work to push the ball up and over to the other platform. So, okay. And then when the little ball here hits this big ball right here, it's going to be an elastic collision. So this ball is going to weigh less than the bigger ball, but it's going to have enough momentum going into it to push the bigger ball the other way and get it up the ramp. So it's elastic because the little ball is going to bounce backwards in the opposite direction while the big ball continues forward in the direction that the little ball was going at first. So I kind of just explained that. The momentum part is it's an elastic collision. In that collision, the kinetic energy is conserved. And again, I said ball 1 is less massive than ball 2. And so the ball 1 will go backwards. And that's what makes it an elastic collision. So then I chose to do a force diagram for when ball number 2 is on this ramp. I did 2 here. I broke it down kind of if you count friction, because really there is going to be friction on, like in real life there's friction, so I kind of broke it down into the 2 things that the 2 equations if you counted friction. But there's not a force pushing the ball up the ramp. It's just rolling, so it is kind of rotational motion, but I just, so without friction, if you're just looking at the ball on the ramp itself, you would take out this this portion of friction. That just ignore that, just pretend that's not in the drawing. So without friction, for just a regular net force diagram, it'd be the normal force going up and the perpendicular to the surface that it's on, and then the force of gravity is down. And so the net force is equal to the mass times the acceleration of the object. So then finally, I chose to do rotational motion for when the ball is rolling down this final teeter-totter. So once it hits this point in the middle, once it hits the point right after it, the teeter-totter is going to tilt. So it's balanced and then it's going to tilt down. That creates rotational motion going as the ball rolls down. And so when it's rolling on the end of the teeter-totter, it starts with gravitational potential energy. When it hits that first point and it tilts, that's your potential energy. So before it starts rolling down is potential energy. That turns into kinetic energy. It turns into 2 different types. It's translational and rotational kinetic energy. And these, the equation for that can be used to find the speed of the ball at the bottom when it finally hits the surface again before it hits the milk. So you can use that the change in energies to find the speed of the ball before it hits the milk and before it lands over and pours the milk into your cereal. So that's the breakdown of my milk machine and the physics that go into making that work. I don't think this would actually work in real life, if I were to be honest, but this is the best I could do drawing wise to try to explain what I wanted to. So in my mind it works, it would work, but there's probably some flaws in my drawing, but I didn't set it up. I didn't have the means to set it up in real life and test it out and see where I would go wrong. But for my drawing, those are the components that I wanted to talk about and break down for physics, and to show kind of that I at least kind of have maybe a basic understanding of what's going on in the physics of when these balls would go through this to dump the milk over. So yeah.